So, as I said in the last lecture, to construct a surface, we actually construct the surface patches smoothly and then map them together in a way the transition maps are smooth. So, as an example, I will do a very simple example, but this is very important if you will carry on your study on differential geometry or topology. That is, we have done this thing before also, a torus. So, we will realize this as a level surface of a single surface patch. Now, remember what was the description of the torus? That you take a circle in a plane and then axis which does not intersect the circle, and you rotate that circle around that axis. So, for convenience it does not matter where we take. So, let me take for that convenience circle in the xz plane. This is the radius b, this is the center, and the distance from the center to and that axis to be z axis, and this distance I take to be a, and of course, I must have b less than a, so that the axis does not intersect the interior of the circle. So, idea is in general rotate circle C along a line L which does not intersect C. So, in this particular case we have taken this circle in the xz plane and L to be the line z axis. So, if you rotate it along the z axis, what will happen? Every point will rotate and I will have picture like, I mean you can try to draw a very fancy picture of a torus through your, I mean you can try, or you can try to generate it through MATLAB or Mathematica, but usually if you see in any lecture, people usually denote a torus by a donut, that is this is a typical picture of a torus. I think I have drawn it earlier also. So, you have to see it from above, and if you see it from above, it will look really like a donut. This is called torus with genus 1. Anyways, that is a language which we are not concerned with. Now, a typical point. So, as we have done before, any point here we will take its projection on the xy plane, then this angle to be theta and this angle to be phi. Then any typical point P on C, the circle where we start, looks like A plus B cos theta. We are in the xz plane, y coordinate is 0, B sin theta. When you rotate it around z axis, then you will, this is a simple exercise, all of you will be able to do it, otherwise ask in the forum that how it is done. Be sure about this example. The entire torus is covered by following 4 open sets and sigma theta phi equal to, let me write it here, A plus B cos theta cos phi. It is very easy actually if you think it geometrically. A plus B cos theta sin phi B sin theta. And what are the open sets? U1 theta between 0 to 2 pi and pi between minus pi to pi, again theta between 0 to 2 pi, this is between 0 to 2 pi, theta between minus, I mean symmetric, and the torus okay. This is a parameterization of torus. There will be many points which are common. Try to identify those common points which will be common to these surface patches, and between sigma 1, I mean sigma 1 and sigma 2 both are covered by certain points, but these 4 patches will cover the torus. And we want to realize it as a level surface of a single surface patch. How? That is done very easily. Suppose I want to denote sigma theta phi as x y z, right, where recall what was sigma theta phi, this is the definition of, this is the parameterization of the torus. Now, if I do a simple calculation, x square plus y square plus z square plus a square minus b square, come back here. So, this is the x coordinate, this is x coordinate, this is y coordinate, this is z coordinate. So, do x square, this simple exercise, x square plus y square plus z square plus a square minus b square. You can see very easily, so you have to check it, this will come out to be 2a plus b cos theta. So, I have to eliminate theta. So, what I do? I take a square again, this will be 4a square a plus b cos theta square, but now this will be 4a square plus 2ab cos theta plus b square cos square theta, which will be, you can easily generate, is x square plus y square. Again this is x, this is y. Okay. Take some time to do this calculation. This part is very simple. I am just eliminating theta and phi. So, this way we realize torus as a single surface patch or as a level surface of a single surface patch. Next we move on to geometry of surfaces. So, by surface again throughout this course, as I said, it will be regular smooth surface. Now, as for the curve, what is geometry? We try to define tangent, we try to identify a surface through its tangent. For recall the curve, tangent, then unit normal, binormal, and then torso, and then finally a curve in R3 is uniquely determined by Fresnel formula that we did last week. So, similarly for surfaces, we want to define tangents, normal, and more of course curvature. So, there are many quantities related to that. As the course progresses, you will see that actually surface will be determined by its fundamental forms, first and second. We will come to that eventually, but let me for time being start with tangent today. So, how do you define a tangent to a surface? Now, surface is a 3-dimensional thing, unless a curve, unlike a curve which is for a curve it was easy, right? For a curve it was easy, space curve or whatever planar curve, you take a curve, take a point and you define the tangent, geometrically it is clear. But suppose I have a surface and I have a point P here, how do I define tangent to a at this point P? Well, I know after all this surface is consists of patches. So, I can consider below it an interval, let us say a b, and a curve passing through P. Smooth curve. So, let us say gamma of some T naught is equal to P. For that curve I can define a tangent, no problem, but immediately you will say okay, there will be another curve, there may be another curve, say gamma 1, define on same interval or some other interval, and I will have tangent, another tangent. So, what we should call a tangent at a point? You understand that I cannot just take one single vector to say something is a tangent, but after all a surface is consists of patches from R2. So, though it is in R3, it is a 2 dimensional thing, right. So, locally it is 2 dimensional. So, what we define here is not tangent, but so called tangent plane. What I mean by that? That suppose S is a smooth regular surface on R3, P is a point on S, the tangent plane T P is the set of tangent vectors at P of all curves in S, all smooth curves. Passing through P, but then it immediately comes to the point that why I am calling it a plane. So, why plane? A plane is 2 dimensional, right. I mean intuitively it will be plane, but I must justify that. Okay. Let us take take a surface patch. Take a patch sigma S intersection W, P in S intersection W, and I can actually forget this W part. I can, if since I am doing everything locally, and let us take sigma u naught V naught equal to P. So, gamma is a smooth curve on S passing through P. So, gamma t will be sigma u t V t, where t belongs to some interval a b or alpha beta as we have written in the board, with some gamma t naught equal to sigma u t naught V t naught, which is P, and I denote that point by u naught v naught. Now, I am looking at the tangent at that curve gamma. So, that is gamma dot t, right. We have done it for the curves. What will be that? I apply the chain rule, sigma u at u t naught V t naught u dot at t naught plus partial derivative of sigma with respect to v u t naught V t naught V dot t naught, correct. These quantities are scalars. So, this is gamma dot t naught is combination of scalar combination of these two vectors. Now, take alpha sigma u, I am not writing, okay, let me write, no problem, sigma u u t v t and consider the curve gamma t equal to then gamma is smooth because it is a smooth surface, sigma is smooth, u and v are smooth. So, gamma is a smooth curve in S, gamma at 0, that is T naught equal to 0 is equal to P, and what is gamma dot at 0? This is alpha sigma u, I am not writing the other part, sigma v. So, what it says that whatever curve I take, this along with the previous page, this one, what it says that whatever curve I take, suppose this surface patch S is sigma u v and my P is sigma u naught v naught, then this set of all tangents, what we have defined as tangent plane, set of all tangent vectors at P for all smooth curves in passing through P, that is in this space. So, it is generated by two vectors, and anything generated by two vectors we usually call it a plane, right. So, that is a tangent plane, and that just justifies the language plane here. Okay. But as I said that everything you define for surface should be invariant under parameterization. So, one must verify, this is a part of a second assignment also, that tangent plane remains unchanged, it is very easy though to do under reparameterization. What will happen is actually if I take reparameterization, then to instead of alpha beta, so you will have some scalar alpha beta appearing depending on the reparameterization. So, the sigma inverse and compose sigma inverse compose sigma tilde at u naught v naught, but check it anyways, it is always better to check it. Now, so we are justifying to call this T p as a plane. So, this is generated by span of sigma u naught sigma v naught, where P is sigma u naught v naught. Now, any plane that passes through origin, right. So, plane will pass through origin. This is generated by two vectors. But whatever passes through origin, some a plane is passing through origin. How can I determine the plane? Then it is determined, this uniquely determined by a unit vector perpendicular to it. So, if I take a point here, or let us take the 0 point. So, if I look at this vector P, this vector, this direction will completely determine the plane, and something perpendicular tangent plane, I should be calling it normal, and I am taking unit vector. So, I should call it unit normal, but there is a little problem here. You can, I may look at it in this way that this is the vector, but somebody standing on the southern hemisphere may say, okay, not this one, the vector is actually the other one in the opposite direction. So, unit normal at point P, either I can define, so this is the vector perpendicular to sigma u and sigma v, and then so if I have two vectors sigma u and sigma v, u naught v naught, then the vector perpendicular to is the cross product, and I normalize it to norm, then what I get is a unit vector. But as I said, direction may be of our choice. I can either choose this direction, you may choose other direction. So, this fellow is up to a sign. So, unit normal, I cannot just define it without mentioning what sign I should put here, and that leads us to the concept of orientable surface, orientable surfaces. So, next lecture I will talk about orientable surfaces. Thank you.